Hello, everyone. So today is a great pleasure for me to present Professor Serena Viti. She has completed her PhD in 1997 from the University College of London in UK in the area of molecular astrophysics applied to the low mass stars. After the PhD, she started working in the field of star formation and astrochemistry. After a couple of postdoctoral fellowships in the UK and abroad, she went back to the UCL with an STFC Advanced Fellowship in 2003, where she became assistant professor. She became a full professor in 2012, and from 2016 to 2020 was the head of the astrophysics group. In 2019, she was awarded an advanced year C called MOPEX, and in 2020, she moved to the Leiden University to take up a professorship in molecular astrophysics. Since August 2024, she also became the designated Earth Chair for Astrochemistry at the University of Bonn, where she will move in October next year to take up the chair. And today she will talk about molecules as diagnostics of dense gas in galaxies.
Thank you very much, Laura, for this introduction. And it's a real pleasure to be here. This is a really wonderful place, and I'm very happy to have been here for a couple of days already, so I could meet and talk with so many of you. And so my plan really is to give a very general overview of the type of work that we do in our group. But before I do that, I am going to give you a general introduction on the field of astrochemistry. Of course, a lot of you here are very, very aware of this field, but in case there are some who do not work with molecules, I hope this little introduction motivates why we care about molecules and why we study them. After that, I will show you how we can use molecules as tracers of not just the chemistry, but also the physics and the energetics of dense gas, and not just in our galaxy, but also in other galaxies. So I will show you some examples in external galaxies for those of you who work in extragalactic fields. And at the end, I really would like to have time to spend few slides on, let's just say, a more recent challenge in astrochemistry, which is the incorporation of more statistical and machine learning techniques as tools to help us in interpreting molecules. So I will probably I'm going to do what I usually don't like people to do, which is at some point, if I realize I'm running out of time, I'm going to skip a part because I really want to make sure that I've got time to talk about this last part. Okay, so this is just a nice collage. Let's see if I remember where yes, here it is. So this is a nice collage of beautiful images of what we can call the multi-million year cycle of a dense gas in any galaxy. In this case, of course, all these pictures have been taken from the Milky Way, and I'm just going to use them as representatives of where you can find molecules. So molecules are not confined to where stars form, but of course they are found where stars are forming, and they're very important for the star formation process. And hence I shall take this multi-million year cycle to tell you a little bit about molecules. And you can really start from wherever you like, really, left or right. If I find the pointer, yes. So I'm going to start from left here. Because I would like to start from what I call relatively diffuse gas. And just to give you some jargon and some numbers to keep in mind, for us, diffuse gas, for us astrochemists, we mean densities of about 100 per centimeter cube and relatively lowish temperature, 10 to 100 Kelvin. And already in this type of gas, in these patches here, these dark patches that you see already a lot of molecules, because despite the low density, there is time for molecules to form. As you know, within these clouds, instabilities will lead to condensations or to collapse due to gravity, and that will form some regions of higher densities, dark molecular clouds, who will be higher in densities, about 10 to the 4 per centimeter cube, but even lower in temperature, more towards the 10 Kelvin here. And out of these dark patches, you will start seeing stars. So these are still cocoon of dust, very famous pillars of creation, being seen, of course, with the Hubble Space Telescopes and now with the JWST. And in these cocoons of dust, you will have the protostar that is being forming. And so temperatures around the protostars are going to start increasing to 100, 200 Kelvin, 300 Kelvin. Eventually this cocoon of dust will be dispersed by jets and outflows from the newborn stars. And again, here now we are dealing with much higher densities, and especially important for astrochemistry to higher temperatures, higher than 500 Kelvin, up to 2000, 3000 Kelvin on average. And so again, you have a circle here of molecular changes, because the type of molecules that will form here are going to be different from those that form here, here, or here. And eventually you end up, of course, that a solar-like system or a planetary system may form, and the densities that you have in this disk around the protostar are very high. We're talking about 10 to the 9, even 10 to the 11 per centimeter cube. And of course, there is a new set of type of molecules that will form. And so what I'm going to talk about now is a little bit about the characteristics of these molecules in these different areas, in these different regions. And I'd like to point out here that, as I said before, you don't need to have a star to have molecules. Molecules are truly everywhere. Often when you see, especially zoomed in, a disk of cocoon of dust with the protostar in the center and an outflow, you can scale that up and you see, physically speaking, something very similar where an AGN. So you have a black hole and a torus of dust, which is the AGN, and jets and outflows that come from the AGN. And there we find molecules too. So we study this as well as gas around AGN and in star-forming region in other galaxies. And we study them with the same methodologies, which is what I'm going to show you in a minute. So again, for those of you who do not work in this wavelength region, we observe molecules from Earth with many beautiful telescopes, both single dish and interferometers, or in the sub-millimeter radio regime. But we also need telescopes in space, because we also need to observe molecules in the far infrared. And for that, we need to get out of the atmosphere, of course. And so we have telescopes such as Herschel and the JWST, of course, now. So what do we do with these telescopes? We observe indeed molecules, and we've seen a lot of molecules everywhere. And I'm going to now show you an outdated list of molecules that McGuire has compiled in 2022, outdated because we discovered, many of you here also discovered new molecules in the last 3 years. This is the first page, and I forget that I've got this I can use. And this is the second page, so you can see that for us astronomers, not for the chemists, I'm sure, certainly not for the biologists, but for us as astronomers, we are getting to really, really large molecules. So even if you forget the last two columns, which I will not talk about, you arrive to 12, 13 atoms. For us, these are very large molecules. To point out, though, that what we do is not just stamp collecting. So we don't, or at least most of us don't just collect molecules. It's important to know that there are so many molecules, but it's also important to know that they are pretty much everywhere up to a certain temperature, of course, after which molecules will dissociate. But this is a list that goes from clouds to high redshift galaxies, where molecules now are routinely observed. And even, in fact, in places that you would think is too hot, like in the surface of the sun, we observe molecules because, in fact, as you know, in the sun there are spots which are darker, and the temperature there is about 3,000, 3,200 Kelvin, and molecules can survive. So there is a lot of water, for example, in sunspots. Okay, so I've told you the molecules are widespread. I've told you that there are a lot of molecules. And so the next question really is how can these molecules form and survive in such harsh environment as the environmental space? And the answer to that is that most of the chemistry is driven by something. So there must be something that helps the chemistry to get kick-started. And one can divide the chemical drivers into four categories. There is starlight, UV radiation, and I will not really talk about that today, or will not talk about the type of chemistry that you find in UV-dominated regions. And the second driver that is very important is cosmic rays. And the arrows there tell you in what type of regions you find each of the driver. So for the case of the cosmic rays, these are very important to kickstart the chemistry in what we call a dark molecular cloud. So this is really a very quiescent environment where the UV does not penetrate because the material is too dense, it's too opaque, and it's quiescent. There is nothing there that can give energy to the gas beside cosmic rays. So cosmic rays is the first driver that I want to discuss, and a lot of you have done a lot of work on cosmic rays. But just to give you a feeling of what type of chemistry you can get with cosmic rays, to start with, as I said, you can initiate the chemistry. So from hydrogen and helium, you can ionize them and eventually forms molecules. So you need cosmic rays to essentially form molecular hydrogen, and then keep going and form all the other species, like CO, simple species. They need this free reaction, essentially, to get kick-started. And so cosmic rays for us are very important because they allow the chemistry to get started in cold and quiescent gas in space. And a lot of work has been done on studying the chemistry, or the effects of cosmic ray in the chemistry as you go deep into the cloud. And in fact, there is work that Asuncion here has done on TMC1 that really shows how the chemistry differs through a dark molecular cloud, a different visual distinction, and mainly due to the effects of cosmic rays. And I'd like to show already, just to give you a feeling of how important cosmic rays are, I'd like to show you here, for example, we could even trace the chemistry of cosmic rays in an external galaxy. So this maps here is the disk of NGC 253. I will show you some work on this galaxy later on, some works that many of you here are involved. So this galaxy is the nearest, one of the two nearest starburst galaxies to us, just 3 megaparsec, I think, away. So it's a starburst galaxy, so a lot of star formation is going on. And what you're seeing here is a map of H3O+, of a transition of H3O+, so an ion, and of SO. Okay, and if you use these two species, you can see that their ratio has a strong dependence, very linear, with the cosmic ray ionization rate. So what you have on this axis is the enhancement of cosmic ray ionization rate with respect to our own galaxy. So basically here it goes from 100 times the galactic cosmic ionization rate to 10 to the 6 the galactic ionization rate. And the different lines are at different temperatures. These are models, of course, and you can see really here, all you need to see is that this is really a very, I would say, quite linear beautiful relationship, which means you can use this ratio to determine the cosmic ray ionization rate in galaxies, okay? And the reason why this is important is because the higher the star formation rate in galaxies, the higher the cosmic ray ionization rate. So, which is something, however, you cannot measure easily directly for a variety of reasons, so I cannot go into it. So, cosmic rays is a driver for chemistry. So for us astrochemists, cosmic rays is really important. Okay, so what other driver do we have? The dust. As you know, there is dust in space. It's only a very little component of space compared to the gas, but nevertheless is extremely important for astrochemistry, as we shall see in a moment. And this particular, there. So, and dust, the dust as a driver is particularly important again as when the gas is very cold and very dense. I'm going to now show you a couple of little movies that have been made by a colleague of mine to show you why dust is so important. And to give you some words before I show you the little movie, the reason why dust is important is that for us it acts as a catalyst because it allows species that in the gas may never meet, so atoms that may never meet in the gas, to meet more easily. Okay, so when you are in a situation where the temperature is very low, the atoms and whatever molecules are in the gas will freeze on top of this dust. And when they freeze on top of the dust, the surface or the distance between these atoms and molecules is going to be decreased. And so they can hop or quantum tunnel, and they can get together much faster than in the gas. There are other reasons why the dust helps, but again, no time to go too much into the details. But what this means is that the dust allows faster formation of molecules and the formation of much larger molecules. And this is what I want to show you with this little video here. Imagine this is your core of dust, silicates or graphite, and species will start freezing onto the dust, and they will get together and form mainly, as you can see, hydrogenated species. And the reason for that is because there is so much more hydrogen than anything else. So an atom of carbon that falls onto the dust is bound to meet hydrogen before it meets anything else. And so you are going to have a lot of methane and a lot of methanol, a lot of ammonia, and of course, a lot of water. So one might say, well, okay, but what do we care about all these molecules in the dust? They're doing nothing for us, except that these are very cold ices that you're forming on the dust. So when a star is born, or where an AGN is powered up, or when you have a strong jet, this material on top of the dust will sublimate back to the gas phase. But of course, what is going back into gas is not what left the gas in the first place. And so you can already see the molecules can help us date the gas, because depending on what you see in the gas, you can have you can tell at what stage of the process you are. What this is showing you is how this material from the dust can sublimate back into the gas phase. There are various ways of doing it, and I will not go again into any details of this, but basically these are all energetic processes that hit the dust and release material into the gas phase. And works on molecular formation on dust is extremely important for complex organic molecules. Many of you are studying on this. This shows an example of a paper by Laura, where a lot of large molecules, again, large molecules for us, are observed in the regions where massive stars are forming. So all these blobs here that you see, you cannot read, of course, what the details of what molecules these are, but they are nicely written here. So these are large molecules and they're compact. The emission is compact and they're tracing really where the star is forming, okay? And so this is telling you that the star is already born and has released the mantle here. It's difficult to, to move this thing. It's released the mantle from our grains, and you see all this chemical complexity in the gas phase. So the bottom line to remember is that dust allows complex molecules to form in space, okay? The last driver that I want to show you in order to finish up this introduction on astrochemistry is the dynamical driver, which essentially is shocks. So shocks will be present, especially if during the formation of a star, but especially once jets are emanated from the protostars. And essentially what you have here is high-density plasma-like material, very hot, impacting on very cold medium. So you can imagine that that you're going to have shock waves, and you can imagine that the shock waves are going to produce a different type of chemistry. And there are two types of chemistry that I want to point out the shocks are responsible for. The first one can happen even in a relatively quiescent type of outflows. So if you have a low mass stars, you're going to have an outflow, which is going to be traced by relatively slow shocks. So this is an example of one L1157, which is a very famous outflows for those of you who study star formation. And we see a lot of molecules ahead here in these various blobs, and those are products, direct or indirect, of shocks. And the type of chemistry that shocks help in the gas phase is what we call the neutral-neutral reactions. These are reactions that normally in a quiescent environment are very slow because they have a barrier, an energy barrier. And so the temperature in quiescent environment is low. And so this type of reactions are not very efficient. When a shock passes, the temperature of the gas increases. And so these reactions become efficient. And so you can have a lot of water, a lot of SO, a lot of molecular oxygen, and a lot of NO in shocked environments. So in the gas phase, shocks allow high temperature chemistry to occur. But there is something else that shocks can do, especially if they are fast shocks, but also slow shocks. And this is that the shocks can spatter the dust grains. And here is works some of you are involved in, which shows, for example, that via certain molecules like SiO, you can witness cloud-cloud collisions. And so without going into the details, but Izaskun can tell you all about it, basically signatures of these cloud-cloud collisions are these emissions of SiO. And the reason why SiO is an excellent tracers of shocks is because silicates are always incorporated into the dust core. So you need something to break up the core, to spatter the core of the dust in order to release Si in the gas phase, which then very quickly reacts with oxygen or with oxygen or molecular oxygen or OH and forms SiO. So if we see a lot of SiO, we are witnessing spattering of dust grains. Okay, so I hope that this has given you a very, very brief overview of astrochemistry. We study molecules wherever we find them, and we find them in very diverse environments, and we can use them to actually trace these different environments, because molecules are formed and destroyed by multiple types of reactions which are sensitive to the energetic processes of space. And hence we can trace back not only the physical characteristics of space, but also the energetic processes that go on in space. That's why astrochemistry is important. So I am now going to talk a little bit about how you can use these molecules to tell you all this information that I told you can get from molecules. So let me then start by showing you what our group specializes in. We don't have pet objects or pet molecules. We just like studying methodologies, or in other words, how can you use molecules to gather and to gain information. So we, as I said, we concentrate on methodologies, and so we work on a variety of models and interactions between models and observations to extract information from these molecules. And what I would like to convince you is that molecules really do have an important story to tell, but you need to be able to interpret them properly. So we use mainly, we concentrate a lot on chemical modeling, but chemical modeling, as I'll show you in a moment, needs a lot of information from the chemists, from chemistry, both from laboratory experiments and theoretical calculations, and also needs to be interpreted these days, especially by using techniques that we borrow from mathematicians and from statisticians. Let me advertise what, again, our group concentrates on, which is in the development and the maintenance of various types of codes. This can be found, this address here, they're all open sources codes. We have several codes, but I will concentrate on advertising one of them, which is called UCL Chem, and some of you know what it is already because you use it. And it's a fairly modular code developed over the years since the 90s, but the most recent release was in 2017, led by John Holship. But in fact, since then, we've added many modules, and a new release will be coming soon, led by Gijs Vermarian, who's a finishing PhD student in Leiden. And so I want to first show you what you can do with a code like that. This code is very fast, and as I said, very modular, which means you can switch things on and off. Things, if you're not interested in certain details, you can switch them off and the code is fast or faster. So this is a type of work one can do with UCL Chem, and this is work that has involved several of you. As you can see from the paper, this is led by Kasia Rutkowska, who's a postdoc in Leiden. And I know that this is a lot of information for those of you who don't do molecules, but let me just give you the main message that I want to give you here. First of all, with this type of code, you can explore a large range of parameter space where you vary the initial conditions by many orders of magnitude. So you can vary the gas density, the temperature, the cosmic ionization rate, the UV field, etc., etc. And you can run this code in different to try to simulate different scenarios, whether you're simulating dark clouds or star-forming regions or outflows. And then what you get millions of these type of plots where you see the evolution, in this case, evolution of every species as a function of time. And the reason why there are a lot of wiggly lines here is because she put everything together in one plot. So she has both, for example, the evolution of these molecules for protostellar objects, as well as for outflowing of shock materials. And what you're seeing the mean abundance as well as the upper and lower abundance. The details don't matter. The bottom line is that through this code, which is public, you can play around and trying to get to fit your abundances. We spend a lot of time in my group maintaining this code or developing this code. I'll show you in a minute. Let me first show you what are the type of plots you can get from this code. Maybe I'll skip this one, but this one could be important, especially for people who work on an extragalactic environment. So as you know, in extragalactic environment, HCN and HNC are two tracers that are used a lot to trace the dense gas in a galaxy, gas that usually is not well traced by CO because CO traces too low density gas on average. And what this type of modeling can tell you really is the relationship between molecules. So these plots here are showing you the relationship between HCN and HNC abundances for a variety of temperatures and for various types of models. So you can get correlation plots, which are not necessarily important for those who study zoomed in objects in a galaxy, but that can be important for those who want to study samples of galaxies. Okay, so what's the type of updates we give to this code? I just want to give you some examples. We do a lot of constant updates on the surface network. What this means, for those of you who are not familiar with it, our codes include both gas phase reactions and surface reactions. So these are the reactions that happens on the dust through the hopping or the quantum tunneling. And so every time a reaction is investigated in a lab by the chemist or in a calculation, we look at it, we insert it, but we don't just blindly insert it in our code. We do sensitivity analysis to really see how important it is. For example, this simple reaction, C plus molecular hydrogen, if you have it on the gas grain, has a lot of consequence. For example, in the case of complex molecules such as glycine, we find that if you allow molecular hydrogen, instead of to just be in the gas phase, but to hop for a few, a little bit longer on the dust, enough to start reacting, we find that abundances of things like glycine, so an amino acid, and precursors of glycine decrease. Okay, so this could be one of the reasons why models used to predict high glycine while we can't yet observe it. It could be that it's actually less than what models are finding. So this is the type of things that we do to update the surface network. We are also doing a lot of improvements on how the atoms and molecules may move on the dust, might diffuse and get together, or may dissolve before they diffuse. So this work is led by Tobias Dicus, don't know if I'm pronouncing it correctly, probably not, who's a PhD student in Leiden as a chemist, and he has improved the code enormously by adding Monte Carlo sample binding energy, updated diffuse barriers, desorption and diffusion prefactors in the equations. I will not go into the details, but if you are interested, this is all treated very well now. And these are again sensitivity analysis to show you how all these different chemical inputs to a model affect the abundances of, in these cases, of ices. So these are molecules observed in the ices by JWST, for example. And I have to do this. And the bottom line of this work, well, there were several conclusions, but two that I would like to highlight here is that the model seems to be mainly sensitive to the diffusions of small radicals. So that's where we should concentrate in study. And actually what we found very interesting through the sensitivity analysis is that in many cases, accurate energy barriers were not essential. So diffusion basically is the rate limiting step. And that's quite important because a lot of people were spending a lot of time measuring energy barriers. And so the fact that for many reactions it's not important could help us reduce the amount of work that we're doing. Okay, we don't just update the chemistry, we also update the physics. UCL Chem is traditionally a 0D model in the sense that it calculates, it is a single point model, but Tram Lengoc, who's a postdoc in Leiden, has updated the physics to treat much better the depth dependence of chemistry from, let's say, the protostar or an AGN outwards. So here there are the details. I don't have the time to go into it, but again, if you're studying complex organic molecules in hot cores, for example, this treatment actually reproduced them much better. And we found that, in fact, if you add the 1D treatment, you can actually trace the decline in complex organic molecules from the center outwards. Okay, so this was just really to advertise this code and the fact that there is a lot of physics and chemistry in this code, and it's very modular, so different people can use it for whatever needs they have. So now let me spend just a few minutes telling you a little bit about some results where we use our methodology. And I decided to take some examples from an extragalactic laboratory. So I'm going to show you some results from a survey, an ALMA surveys of this galaxy, NGC 253. So let me pass straight away to the details of this galaxy, of the survey. So many of you are part, or some of you are part of this survey. It's called Alchemy, and it's a spectral survey of the disk of NGC 253. So if you see all these blobs here, these are giant molecular clouds that are part of the disk of NGC 253. This is a very, very nice and very busy spectrum. And the message here is that we can now do chemistry outside our galaxy. Okay, there is no doubt. Okay, so every line is a real transition. And so what we need to ask ourselves is not whether astrochemistry can be, whether there is astrochemistry in external galaxies. The question we need to ask us is, what can all these molecular lines tell us in extragalactic environment, where of course the beam is much larger than the beam that we have in our own galaxy. And so again, I've just picked some work which I think at least some of you would be interested in. Sulfur, for example, many of you have studied sulfur, done work on sulfur. So Mathilde Bouvier, who's another postdoc in the group, she has concentrated on studying all the sulfur-bearing species in the central molecular zone of NGC 253 with the aim of trying to reconstruct the history of star formation in the center of the galaxy. And although I won't have time to explain why sulfur is important, I think you can ask many here in the audience why sulfur-bearing species are important, but trust me, they are important as species. These are the maps of several lines of several molecules of sulfur, and it's very important to observe many transitions of as many species as you can, because although you might not be able to see the details, I hope that you see that the blobs are different. Okay, so each molecule and each transition is tracing different components. And so in this particular work, everything was analyzed, everything was compared with objects in our own galaxy. So here is a comparison of all the sulfur-bearing species in NGC 253 with regions in our own galaxy, shocks, hot cores, so apologies for the jargon, and molecular clouds. And the conclusion is this nice little drawing here that represents one molecular cloud in the disk of NGC 253 in the outer zone. So imagine if this is your disk, we're looking at the molecular cloud there, and one in the inner molecular zone. So two different giant molecular clouds, so representative of two different giant molecular clouds, lots of labels, lots of colors. Of course, don't expect you to look at it now, but I hope that the message here is that this multiple colors and multiple drawings and geometrical shapes means that the different species are tracing different components. So we can trace shocks within the geomolecular clouds, we can trace where the stars are forming, and we can trace the temperatures and the densities by collecting and analyzing together all these sulfur-bearing species. And two of the conclusions that I decided to pick out are the following, that H2S is a particularly nice and unique trace of the highest density across the central molecular zone, and that most sulfur-bearing species in at least this galaxy are tracing shocks, but not fast shocks, but slow shocks. So it's a nice, nice category of species to trace the shocks that don't leave as a signature a high abundance of SIO. So slow shocks could be traced by this. Equally, Mathilde also worked on complex organic molecules in NGC253. And again, without going into details, the usual intensity maps here that are showing you the different complex organic molecules are tracing different material. And then when analyzed all together, and again, I'm not going to give you details of the very long analysis that was done, you can create pictures like this, where you can pinpoint in one giant molecular cloud the different physical components, from cloud-cloud collisions to stars, outflows, and even trace a different type of origins for complex organic molecules. And what is nice here is that we found that a lot of these complex organic molecules may actually be formed, or at least augmented, by gas phase reactions. So not just from the dust, but they might form also in the gas. And the one conclusion that I want to highlight from this work, among several, is that if the complex organic molecules are emitting at giant molecular cloud scales, because of course they may be emitting from a smaller region and we cannot resolve that, then the most favorable scenario to explain their widespread emission is that they are tracing very large scale slow shocks. And this actually resembles what is seen in the center of our own galaxy, so it's not too surprising, but this is for an external galaxy. So I decided, since I only have 6 minutes left, that I'm going to skip the next part because I want to talk about the work that we're doing with statistics. So let me just pretend you're not seeing what I'm doing. I always hate when people do this. Yeah, well, and let me go to the last part of the talk, which is what I call the modern or latest astrochemical challenges, which can be summarized in these 2 red boxes. The first one is that if you are interested, for example, so in complex organic molecules, and you've seen that they can form on the dust grains, we don't have the luxury for most of them to determine values of their frequencies, their intensities, their formation routes, their rate coefficients through experiments. And so we are slowed down by the fact that we know very little about these complex organic molecules. If you don't care at all about molecules, but you do care about galaxies, and you want to understand star formation rates and star formation efficiency in galaxies and where stars form, your challenge here is that for most galaxies, we do not have the luxury of multiple lines observed for multiple species like we did for NGC253, which was very close by. And so you may observe CO and HCN, but I hope I've shown you, I've given you enough evidence that it's not enough to observe one molecule to understand the dynamics of a galaxy. And the reason for these challenges, again, is expressed in this very simplified sketch, that essentially astrochemistry is dealing with a lot of physics and a lot of chemistry and energetics, and these two are interacting with each other in a very complex, time-dependent, and non-linear way. Okay, so this is our problem. How do we tackle these problems? Well, before telling you how we could tackle it, I need to break it down into bearable challenges. And so I've decided to do it in 3 main challenges, also seeing what people here are working on. So the first one is, ideally, we would like to be able to determine, without relying too much on experiments, we would like to determine the most likely pathways that lead to complex organic molecules, with the aim eventually to understand whether amino acids can form in space and whether they're present. The second challenge is that ultimately for most of you, for those who are not astrochemists, you don't care about the chemistry, you care about the physics of the universe, but and so you care more about modeling, for example, using hydrodynamical models from the early universe to star formation, to understand how things are happening in the universe. But you cannot do it really without chemistry. You can ask me later why, but chemistry is too slow. So you need to sometimes forget chemistry and emulate it in order to plug it into hydrodynamical models. And the third challenge can be rephrased like this, that as the further away you're looking, the higher redshift you're looking, the larger is your beam, the more components, basically, not the larger is the beam, but the more components are inside your beam, you find sometimes the whole galaxy in your beam. And so you need a way of blindly disentangle and characterize the multiple components of interstellar medium. So let's see. The first challenge can be approached by reducing the chemistry. So you can do that with various ways, which I list there. What on this slide I'm showing is a work that Johannes Hale has, a few works that Johannes Hale has led, was a data science PhD student, and he explored and exploited network topology. So basically all he means here is that he found ways. So again, I'm not going into the details, but just give you the conclusion. So basically, he found ways of reducing networks. So if you imagine this is our toy networks to lead to the formation of methanol, water, CO2, and CO on the ices. He found ways of splitting the networks and having sub-networks, okay? And for this particular work, we found that the place where you need to split it is the point with the highest network connectivity, and in this case, it was the CO molecule. And again, in no details, but it allowed us to reduce the number of reactions. So this is one approach. The second approach is via Bayesian inference. So what you do, you run millions and millions and millions of chemical models, and then you look at and you run them with a network where you vary the rate coefficient of each chemical reaction by many orders of magnitude. So this is going to tackle the problem that we do not know the rate coefficient for species, for reactions, especially on the dust. So what we did here was basically looking at the posterior probability as a function of a variation of a rate coefficient of different reactions. Yes. And what you really want to look at is this. Basically, the density, this PPD, this posterior probability distribution, will reveal the areas where the reaction rate is the most probable. But the important bit is this. If you have a uniform probability distribution, so like here or here, basically means that this particular reaction is not impacting the likelihood of a model. It means that it's less important. While if you have a peak like this, then it means that this reaction is really important to really be able to, you need to determine basically the reaction rate accurately, because this reaction, if you go too far away from the right rate of a reaction, then you get the wrong answer. And finally, no, let me skip this. And finally, you can approach the reduction of chemistry using machine learning. So in this particular case, this is work led by Gijs Vermarian, who at the moment is also the one leading the development of UCL Chem. So with machine learning, you can use, for example, this method here is sharply additive explanation. I don't have the time to go into details, but essentially it's a method to interpret machine learning results, which allows you to give importance to the various parameters, to the various molecular abundances. So in other words, it's telling you what parameter, what physics is important for each molecule. And it gives this number here, which is called the normalized shape importance. Again, I don't have much time to explain it, but another way of seeing it is you might have seen this type of plots where basically you see whether it's the bigger bulb is the importance is giving you information on the importance of a different parameter. So what you're seeing here is gas density, initial abundance of carbon, temperature, UV, cosmic ray, and this is the sharp value. And this for each of the ratio, H2C over methanol, Cn over HCN, you're seeing what is the parameter that is most important to determine this ratio. So for Cn over HCN, the density is key. For H2C over methanol, the temperature is key, which is not surprising in the sense that empirically we found that H2CO is an excellent tracer of temperature, for example. And I should point out, oops, no, what have I done? Hang on. Sorry, I need to go back, but I'm not managing to go back. 1 second. It got stuck. Ah, yes. Okay. Also, in order to interpret machine learning works in astrochemistry, we're also using this UMAP, this uniform manifold approximation projection technique. Again, it's a reduction method to create intuitive groupings of models. So all these techniques that I've shown you example of are in order to somehow reduce the complexity of the chemistry, okay? So that's the message really here. Okay, so the second challenge was basically create emulators, forget the chemistry. Can we forget the chemistry? In some cases we can, some cases we can't. But anyway, we have built various emulators. So this is one, this is for, it's called neural PDR, and it's an emulator for a type of model that tackles photodominated regions. This is particularly important for extragalactic studies because extragalactic studies, when they often detect large-scale photodominated regions via observations of carbon or carbon plus or CO. And we can emulate, instead of using proper photodominated region models, which are very computationally expensive, we have created this emulator based on neural networks. And here they are the nitty-gritty details for those of you who understand this. I don't. Again, led by Gijs. And we've done the same for to emulate the UCL Chem and also RADEX, which is a radiative transfer model. So maybe many of you use. And this is work led by Damien de Mijola, and was a PhD student in data science at UCL, and John Holship. And again, these are showing you violin plots of the error between essentially the abundance that you get between UCL Chem and the emulator of UCL Chem. UCL Chem, remember, is a chemical model. And here the differences in intensities between RADEX and the emulator of RADEX. And then it was tested on a real set of data from the galaxy NGC 1068, which is a composite galaxy with an active AGN observed to death in many species, especially HCN, HCO+, and CO. Oh, and I'm late. Okay, so third part, how to speed the chemistry. So we have reduced the chemistry. I've shown you how to forget the chemistry, and now we want to speed the chemistry. And this is another work led by Damien de Mijola, which essentially is found an algorithm which is called NMF, non-negative matrix factorization. Again, don't have a time to explain it, but essentially allows you to blindly decompose. So if you look at a galaxy and you have a beam, which is say as big as this box, and the emission is made up of 3 different components. So let's assume this is the real observations. This algorithm can retrieve these 3 different components, and it can do it for a variety of molecules. Finally, I want to show you this last work again by Gijs, was, oh, never mind. It was called the Carbox, and it's a quick and dirty, but very useful end-to-end differentiable astrochemical simulation framework. And essentially what it is using a modern high-performance framework called JAX, which can utilize GPU acceleration, and so allows you to, they do sensitivity studies. So basically it's so much faster. It's not an emulator, so it's a chemical model, but it's much faster than the standard chemical model. And so you can do really, really very, very, very fast sensitivity studies on multi-dimensions, which is one of the problems when you do sensitivity studies. And the dotted line is the output of Carbox, so fractional abundances, and the solid line is from UCL Chem. You can see that they are very similar, even when they're different here, but we're talking about super, super low fractional abundances, so we don't care about these differences. Okay, and I am done. I'm going to leave you with my concluding slides, with my key messages. Thank you.
Thank you very much, Serena, for giving us this review on chemical models and what you are doing in your group. It's a nice time for questions. Wow, a lot of hands. So Victor and then Gabriel.
Thank you very much, Serena. It's impressive the amount of work you are doing in your group, putting together observations, modeling, and data science. So I have a couple of questions about the last part of the talk. So I was wondering, because you didn't have much time to explain, if you can give us more details about the SHAP analysis.
Yeah.
And what is the philosophy that uses?
Oh, sorry. Let me first find how to go back. Yeah, no, I lost the, give me 1 second, and okay. It's now. I can't, I'm failed by technology, so I'm not sure I can tell you much about sharp values, but let's see if I manage to get there. Okay, almost there. Yeah. So I can tell you what I understand of SHAP, okay? Because I refer to Heiss for my data scientist that does this thing. But basically, what the SHAP technique does, it gives you a prediction value, which is this number that you see here, among all the different features. So what it's doing is grading the features, right? So you imagine you've run all your millions of models through machine learning techniques like emulators or other machine learning to accelerate the inference, whatever, right? And then you use SHAP to grade the importance of the feature. For feature, I mean density, temperature, cosmic rays, whatever, for each of your molecules or a ratio of the molecules. And this SHAP was created as a game in game theory. So basically, it was showing how each player would contribute to the result of the game, right? So I don't know many more details than this, but I think this is, in my opinion, the one that I understand most. But to show it, to understand it, or rather to tell you, I need to read the caption because I forget the colors, very important. So this is called the B-swarm plot. And so again, it's showing you the relative importance of all the different physics. And this is measured by the mean of the absolute value of the SHAP value averaged across all the predictions. And so the colors, let me see, because I never remember. So color-coded is, they're color-coded in terms of the size of the feature value, so the density, temperature, etc., and relative to the range of the values that the respective feature takes. So, for example, I think I like to take the Cn over HCN values. What is telling you whether it's the blob there is that a lot of the models fall into that value. this is these sharp values. But the blue, let me see if I can. Yeah, so the blue and the red are just really pointing to those that are positive or negative, essentially, for the ratio. I'm not sure. Yeah, I'm not quite sure how. I'm trying to find other examples that people have given me of the sharp values. But apart from the game theory, I cannot think. There's another example Gijs often gives on people in a taxi that share the fare, but I don't remember, I have to admit. So I don't remember the sharp. All I know is that for us, what is important is the bar there that is showing you the low and the high value of sharp. When it's high is what you're looking for, basically. So it's the strongest correlation between a feature and a ratio or a molecular abundance is the high, is the red, basically.
So red is telling you that that feature, so that parameter is important, is playing a role in that ratio.
Yes, and there are all sorts of other layers to this sharp interpretation, but that's what I get out of it, yes. Yes.
Okay, thank you. And the other question was about the cat box that you show in the last one. So this is a chemical model, right?
It is a chemical model.
But you mentioned super fast. So what's
super fast? Because what it's doing is using this framework called JAX to rewrite the ordinary differential equation. So this is instead of writing it in Fortran or in Python or whatever, it uses this framework, which is, I think, a very, if I'm not mistaken, it uses Jacobians and is optimized, again, don't know the details of the technical part, but it's optimized for high performance. And you can utilize GPU. So at the moment, if you take UCL Chem, you cannot really run it with GPUs. It doesn't help at all, right? You need CPU. GPU are much faster, right? And so with this way of writing the ordinary differential equation, so it's a mathematical framework. With this way of writing the differential equation, you can use GPU. And apparently, so that's why I say there, you can study sensitivity much better, because we have sometimes the multi-dimension. If you take a rate of a reaction as a dimension, we are working in thousands, in a dimension in thousands and thousands, right? And so you could, in principle, run sensitivity with this type of, this is, I think Gijs put it public somewhere, so there is an address for it. And he says that it's much easier to interface it with the machine learning modules. So it's, yeah, it's a quick and dirty way of doing analysis, sensitivity analysis.
Okay, thank you.
So.
Okay, hello, thank you.
Too many technical questions. I'll refer you to Gijs for it.
Okay, yeah. No, also I was referring to the part of machine learning. Just was wondering to know what was the input that you gave for the training, especially for the dimensionality reduction. Okay.
So for everything I showed you, we use UCL Chem as if it were perfect, which of course is not. In a sense, we use UCL Chem, the classical version, to create all the training sets and the test sets. In some cases, like for the emulator, then we, of course, test it also on real observations. But a lot of these works are all proof of concept works, which I would like to take to the next step. So I find someone, I'll take them to the next step, and of course, test it and iterate it with observations. But at the moment, the training sets are mainly done either with UCL Chem or, in the case of the neural PDR, with another PDR code that we have, which is called 3D PDR.
Yeah, because in the UMAP algorithm, the data is also related with the diversity of data and the quantity of data that you're giving as an input. So probably the sharp values are also going to be related to that.
Exactly. Yes, absolutely. Yes. Yeah. So we show the UMAP. I didn't show the UMAP because, well, you found a really nice way of showing the UMAP. We have them in the paper, but to me, they're very complex to explain, and it would have taken me 10 minutes to explain a UMAP map. So maybe I'll show it to you later if you want. But yes, indeed, UMAP is...
Okay, and was one last thing about the computational cost of training these models, both in the dimensionality reduction and in the CNN. How much time or...
It really depends. We have to use clusters, national clusters for some of the work of this. Some can be done on our, we have a number, I don't remember, I have a cluster of few cores, I don't remember the number of cores at the moment, and we can use it for some of the testing, but for really creating the large training sets, we use the national cluster. I cannot give you values because I don't know, but sometimes, especially for the PDR part, you can take even a month or two.
Okay, thank you.
A lot of time. Hence this card box eventually. So Heis got frustrated, which is why he created this card box as a side project, because he was frustrated with the amount of CPU time and real time that he was spending on training.
Okay, thank you.
Any other question? Okay, so Asuncion.
Okay. Thanks, Serena, for this nice talk. Well, I have many questions, but only 2 questions. And have you tried to create to fit directly the line intensities, not to fit with a neural network the abundances, and then with Radix predict the line intensities, just to skip this step and go directly from the input to the line intensities?
So without the chemical model? Yes,
no, with the chemical model, but just, okay, you have a given density and temperature, and
yes.
then you predict the abundances, and then
yes.
you predict line intensities,
yes.
and then just make all the thing in one step. You give the line intensities, and you need to retrieve.
No. So most of the work, which I couldn't really show all of it, but most of the work that we done for alchemy, so for NGC253, it was done like that. So it was done running UCL Chem, then feed the abundances to Radix, and then feed the intensities from Radix.
Okay.
Yeah, but most of the work that I've shown you for NGC253 were done like that. Okay. So nothing of that. Yes.
Okay, and the second question is about the UCL chemical code, because, okay, when you go to very extreme conditions, I am always worried about if our chemical networks are good enough.
Yep.
And for instance, if you go, you want to model a hot core with temperatures of 500 Kelvin and densities very high, do you think that the chemical network is good enough to account for this condition?
I think having looked at reactions available in the gas phase, that is from the databases like UMIS or CAIDA, I think up to 1000 Kelvin, most of them are, or at least some of them are calculated or measured. In some cases, indeed, they're extrapolated, and that is the problem. A lot, the ones that are not calculated or measured up to 1000, they are up to 300 Kelvin. So for hot cores, I think we are okay. When we go into the regime of shocks, I agree that we may be missing some, not missing, but wrongly allocating a rate coefficient to reactions. So indeed, the chemical models, I should say that at the beginning, but I say now, chemical models are only as good as the databases that feed these chemical models. But this can be sometimes circumvented, for example, from sensitivity analysis, in the sense that one of the reasons why we do all this sensitivity analysis is indeed for the reactions that you're mentioning, because if we have n number of reactions for which the reaction is unknown or not well constrained, if we find that only n minus m are important, we only need to care about those. The others, we don't care that we got them wrong because they are not as important. No, they're important in the sense that you need to have them to form the molecules, but the rate can be wrong by 1, 2, or 3 orders of magnitude. It doesn't matter too much, right? And that's what we are finding. That's why I think sensitivity analysis are essential. Every time a new reaction pops up from a lab, or sometimes not from a lab, but from the invention of one of us, right? It's okay if sometimes you're sure that the reaction is present, but you have no clue about the rate coefficient. So you need to assess the importance of getting the rate coefficient right.
Okay, thank you.
Thank you for your talk. My question is much more naive, I think. Just out of curiosity, I guess that UCL Chem provides the initial conditions for those simulations depending on the astrophysical region. So I guess those initial conditions are also based on other models, or are they detections? Like, how do you know? And what's the level of uncertainty?
No, it's a good question. You can use UCL chem in an inverse or a forward way, in the sense that you can get the constraints from your observations and feed them in it. And also you take those input parameters as fixed, let's say, and as real. Or you want to do the other way around. That's exactly what you want to fit. You want to derive from your region the physical parameters. So you want to use molecules only as tools. You don't care about molecules. You can throw them away later, but you want to use them in order to discover the gas density, temperature, etc. So at that point, you vary them, and you have to have a large grid of models so that then you use the molecular abundances and intensities, the theoretical molecular abundances and intensity to fit with your observed data and see which parameters best fit, right? So you can do both ways. So they are the input parameters can be both fixed and not fixed. Yeah. Was that your question, or did I misunderstand your question?
Yes, but I guess if there is uncertainty in the parameters are in the also in the detections, that would be transferred to the uncertainty in the initial conditions and the other way around.
Oh, the other way around. So yes, so you're talking about the uncertainty in the observations.
Mm-hmm.
So that for us actually we translate it. So what the uncertainty in the observations give you is an uncertainty in the, let's say, the abundance of the molecule, right? And so we take that into consideration when we do our best fits, which you can use several methodologies to do the best fits by Bayesian inferences that we usually use. And so you take into consideration the error bar of your abundances. And so then what you tend to get is indeed a best fit of density temperatures with an error bar as well.
Okay, thank you.
Thank you very much for the great talk. I was also curious about the Carbox and the JAX, and yeah, I just wanted to know if Carbox has, so does Carbox has the same functionalities as UCL Chem, or it's still like?
Well, we haven't tested it. This is always proof of concepts, which we haven't tested properly. But here you can see for this particular model, it's this, I think, if I remember correctly, let me think now, it was so these are two different models. One is a hot core, and the other one is a dark molecular cloud, I don't remember. And so he has the same functionalities. But what I don't think he has, I don't think at the moment has all the physical modules for it. But I need to check. I don't remember. This really just came out very recently, like the last few days. So I inserted this at the last moment. And so I need to, this is something that really Gijs did for himself. So I need to talk to him about it because I think it's more of a toy model. I think it's the complexity of the physics at least is reduced. Yeah.
And how much is the difference in time for computing?
I don't remember that either, but a lot. A lot. Yes.
Wow.
I mean, one model takes a few seconds at UCL Chem. So it's when you do large grids, it's a lot. When you go from CPU to GPU, it's a lot. It really accelerates it a lot. Yeah.
Mm-hmm. Okay, very interesting. Thank you very much.
And I think we have a question on Zoom.
Yeah, there's a question in Zoom, which is, I was wondering if you are also using the sensitivity analysis to orient the direction of laboratory and computational studies.
Thank you very much for the question. So indeed, not only we're using this was originally why we did the sensitivity analysis, it was exactly for that. So being not an experimentalist, we were very frustrated by the length of time that in the lab it would take to do one reaction under one set of conditions. So that frustration led us to try to use this reduction techniques of machine learning to work out what reactions are the most important for the lab people or for the computational people to concentrate on. And in fact, some of the work that Juan Enrique Romero has been doing together with Tanya Lamberts is with a system that we told them that we wanted them to look at because it was very sensitive. So indeed, that is one of the main reasons why I think it's important to do sensitivity studies.
Okay. So I think we can stop here and thank again Serena for being here. So see you after Christmas.